What's up, everybody? It's Dan from SageMathTutoring.com and here with a video going over some pre-calc concepts. This is based off of a test that a student of mine took and some wrong answers here and there. And we're just going to go over them. So let's take a look. Describe the conic. All right. So I think I want to just focus on the problem only. So let's take a look. Describe the conic, give the coordinates of its center. Okay. Yeah, so my student is probably recognizing you're going to have to complete the square in order to find out what this conic is. At the very least, you're going to want to get the non-constants on one side and the constants on the other. After doing that, you would have a 20 on the right. We could say minus 8x minus 3y squared plus 12y. So already I'm seeing opposite signs for these, and also the coefficients are different. So I'm pretty sure that's going to be a hyperbola just based off of that. Nonetheless, we do need the center, so I think my student is recognizing that that will be a matter of kind of maybe factoring out the GCF of the first two terms, or we could say the X uh, related terms, and factoring out the coefficient, the GCF of the Y related terms. And that would be, what would that be? Minus 4. Why? Now notice how I'm kind of leaving a space here for the special number that we're about to bring in. And the special number will always be this middle coefficient divided by 2 squared. So negative 2 divided by 2 is negative 1. Negative 1 squared is positive 1. Uh, Negative 4 divided by 2 is negative 2. Negative 2 squared is positive 4. So that is the case. Now, here's the thing where I'm kind of thinking maybe my student did wrong. Oh, I see. I see. Yeah, we'll get to that in a moment. So, what you do with this is you have to acknowledge that what you actually added to this left-hand side when we kind of added this 1 here is we actually added a 4 times 1. Okay. So in other words, we added a 4. Now, for my student watching, just know that the way to kind of make up for the fact that you just added a 4 in this moment is you add it on this side to even it out. Okay, so uh, when you're completing the square to create the equation of a conic, the completing the square process is a little bit different in that you do actually want to kind of, balance things out on the other side. All right. Um, Now, if you're completing the square for the purpose of turning a standard form um, quadratic function into a vertex form quadratic function, then that's a different story. But anyway, either way, we're really adding a 4 here. So therefore, we have to balance things out by adding a 4 there. And I think my student watching probably knows that we really added a negative 12 here. So we have to balance that out by making a negative 12 over here. As a result of that, we will have 4 times something squared minus 3 times something squared, and that's going to equal 24 minus 12, aka 12. In the parentheses here, it's going to be x minus 1. So for my student watching, if you're ever in doubt as to what this number is, it's always going to be half of that middle coefficient. This is going to be y minus 2. And then we're ready to do the thing where we want 1 over here because the bottom line is this coefficient is different than this coefficient, which by the way is the sign that it's not a circle, just so you know. The moment I saw, for example, that this 4 was different than this negative 3, because the 4 is in front of the x squared, the negative 3 is in front of the y squared, in that moment I knew it's not a circle. And the moment I saw that the signs were different, so this is positive, this is negative, then I knew that it's going to be a hyperbola. Okay, so this is a hyperbola. Now, hyperbola conic sections always have a 1 over here. So hopefully, my student watching understands you will indeed be dividing everything by 12 right now to force that right-hand side to be a 1. Now that becomes 1, that becomes 3, that becomes 1, that becomes 4. Next thing you know, we have x minus 1 squared over 3 minus y minus 2 squared over 4, and that equals 1. And then the center is 1 comma 2. So that should be the answer. Looks like in the attempt to kind of balance things out, my student did a +1 here and a +4 there. And I totally understand why my student did that. But this is, you do something along these lines if you're trying to convert standard form into vertex form. And that's not the task that we're presented with. Okay. If you're turning the standard if you're turning a conic equation into standard form, then you want to do it the way I just did it. Okay, so that's that. Find the inverse of this function. Okay, let me see. So for this, my student watching knows you, yeah, you want to kind of treat this like y, and then treat and then do a little switcheroo where that's x to y minus 1 for y plus 3. At this point, yes, you want to get y by itself, and really the smart way to do that is to multiply both sides by 4y plus 3 to kind of uproot that denominator. So that's gone. Now we have 2y minus 1 equals this whole thing. But, this right here is such that we can distribute, and believe it or not, we should, even though this can result in sort of an ugly situation. So we have 4xy plus 3 x, and that equals 2y minus 1. Now let's remember, we are trying to get the y by itself, and in order to do that, you want all the terms that feature y on one side and all the terms that don't feature y on the other. So hopefully my student watching understands that will be a matter of subtracting 2y from both sides. And by the way, let's get this over with. Let's subtract 3x from both sides. Now, as a result of that, hopefully we all understand that will be 4xy minus 2y equals -1 minus 3x. Uh, and that is because these canceled, pardon me, these canceled, these canceled. Um, Then the purpose of getting all the terms that feature y on it on one side is to factor out y as the GCF. Then we have 4x minus 2 equals this over here. At that point, you can divide both sides by the 4x minus 2. So this is how you go about these. All right, next thing you know, you will have y equals really just this thing. Um, and I think the teacher would probably accept that as it is. I don't really think you have to factor out a -1 or anything. You can't simplify this, you can't reduce this, so you are kind of stuck with it. Now let's be clear, these canceled. So that is how you do those. Okay, so let's see. We'll get rid of these and look at the next thing. Find the domain of each of the following functions. Your answer should be given using symbols with the basically the inequality symbols. Okay. All right. Well, hmm, hmm, hmm. Right. Looks like the teacher doesn't want interval notation unless. Okay, so I guess this is the teacher's way of saying the teacher wants interval notation or is willing to have interval notation. Um, yeah, so when finding domain, um, hmm, there are two broad scenarios you need to be on the lookout for. And when it comes to whether or not there's a restriction on the domain, and those scenarios would be uh, rational functions where you have an x in a denominator somewhere, and radicals where you have an x underneath a radical, and then occasionally there might be a scenario where you have a combination of both, which is a little bit more nuanced, but it turns out that we don't need to worry about that here. What you sort of do and understand as it pertains to the rational functions is a little bit different than what you do and understand as it pertains to the radical scenario. So let's focus on the rational scenario, meaning there's an x in the denominator. All right, and when I say rational, I mean this is a rational function, not a rational number, a rational function. So a rational function is a function that sort of has an x in the denominator like this. It's a variation on this parent function. So looking at this one though, all you need to know for this is that the denominator is just simply not allowed to be zero. Now, I have my own way of sort of cutting to the chase with that. I like to literally just say, okay, fine. So x minus 3 under no circumstances can be equal to 0. So just personally choose to use a not equal to symbol rather than an equal symbol. Other people, including the teacher, might temporarily just treat this as its own equation with a regular equal sign, and solve it and then kind of take it from there. But I like to just remind myself out the gate that this thing can't equal 0, but then I treat it like an equation and I quote unquote solve for x here. So this would be, of course, a matter of adding 3 to both sides. And next thing you know, you have x cannot equal 3. Now, it does appear the teacher is using number lines, which is good. I kind of like that. And then it says from 3 to infinity. Yeah. Okay, that's fine. Okay. Now, what does this mean? X cannot equal 3. Let's just pause for a moment. What this means is that X is allowed to be anything except this. That's all this is saying. And I think my student watching understands probably where we're going with this. That means that there is a hole here, but everything else is filled in. Now, I like using number lines like this to represent the domain because it's very easy after graphing your arrows on the number line to write your interval notation because you want to have interval notation for each arrow. So the arrow on the left, what's that communicating? Well, what's the leftmost point communicated here? Certainly infinity. What's the rightmost point communicated on this arrow? Certainly 3. What is the leftmost point associated with this arrow? Certainly 3. What is the rightmost point associated with this arrow? Certainly infinity. Do we get a parentheses or a bracket next to infinity? Always parentheses next to infinity symbols. Do we get a parentheses or a bracket next to the 3? Well, in this case, it's a parentheses because the 3 is not included because there's a hole there. The same reasoning applies to this and this. And this is your answer. However, your teacher wants you to join these, I'm sure, with the union symbol, um, and that would be the official way of writing the answer to that one. Okay, so I'm sure my student can already see what went wrong there. Um, Basically, only focusing on this part, it appears, 3 to infinity, disregarding the fact that this part is included. I think Also, for my student watching, what you're doing is you're doing a plus minus graph thing. Um, that only applies for inequalities. Now, this was like inequality symbols, like greater than or less than symbols. This is not a greater than or less than symbol. Okay. This is a different type of approach when you have rational. For my student watching, what you're thinking about here has more to do with what you do with a radical. So, what do you do with a radical? Well, you acknowledge that whatever is under the radical, whatever that is, has to be greater than or equal to zero. Now, it can be zero. That's totally fine. It can be zero, but it can't be less than zero. That's what's being communicated here. It can be more than zero. It could be zero, but it can't be less than zero. And that's the thing you have to remember always for finding the domain when you have a radical. What you then do, what I would advise is temporarily treat it like it's an equation. It's not an equation, it's an inequality, but treat it like an equation. And thusly, you would factor it for my student watching. Yes, 4, 5, it would be minus plus x quote unquote equals negative 4x quote unquote equals 5. Now, what we found there are the critical values. Okay, so once again, when you have an inequality like this, um, you can kind of temporarily treat it like an equation, and the purpose of that is to find your critical values. Now that we have the critical values, you draw your number line and you can plot them. You have negative 4 and you have 5. Um, since this is a greater than or equal to symbol, that means this thing could indeed equal 0, and therefore you have closed circles there. Okay, greater than or equal to, this little underline means it's closed circles. Okay, now you do your test. Okay, you do your test. You can pick maybe 0 to work with, negative 5 to work with, and 6 to work with. And you basically just see what happens when you plug these green test values into the original inequality. Now, I'm already foreseeing, I'm going to do something relatively advanced, which is to rewrite this inequality. But I'm just going to actually rewrite it in factored form because I could already see that this is going to be a little bit easier to do this next part. And we're going to work with that sort of factored form. But keep in mind, this is still an inequality. In the green box, we temporarily treat it like an equation. But over here, we're kind of leaving it as an inequality because we want this for the next stage of the process. So then you do your test values. You plug in negative 5 into this, and you see if it ends up being true. So when you plug in negative 5, you will get a negative 1 and a negative 10. Negative times negative is positive. So that's going to give you a positive result there. Um, when you plug in a 0, you will get a 4 times a negative 5, which gives you a negative result. So that will be negative. And finally, when you plug in a 6, you are going to get a 10 times a 1, which is a positive result right there. Now we're looking for the places on this graph where it is greater than or equal to 0. And we already know where it's equal to 0. It's equal to 0 at negative 4 and 5. But where is it greater than 0? Well, it's greater than 0 anytime you have the positive values, right? So hopefully my student is seeing that we are therefore only going to graph with regards to arrows, those areas where there is a plus sign. So where are those areas? Those areas, of course, are here and here. So using interval notation, we're looking at negative infinity to negative 4. We're looking at 5 to positive infinity. Always a parentheses next to infinity. 4 is included this time, therefore it gets a bracket. Similarly, bracket here. and infinity, and then you have the union symbol in between, and that should be your answer to that other function with regards to the domain of this one. So let's see. Um, -4 and 5. Oh, okay. My student watching, good job, first of all. Yeah, you just factored it wrong. Okay, so this might have been a lot of unnecessary stuff, but hopefully, I don't know, it reinforces it. So that's how you do that one. Solve the equation for that time, blah, 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 blah. Hmm. Well, I mean, you could use a calculator for that. If you were to use a calculator to solve this, you could say y equals 0. You could say y equals this, and then you could graph both of these and find out where they intersect. That is something that most definitely could be done for this. And it is the case that you need to be in radians, though. So you'd have to go to mode probably and just make sure you're in radians. Radians. Um, because these are radians. All right, so if you were to do this algebraically, like without a calculator, um, they're actually kind enough to factor it for you. So what this means is sine x minus 1 could be 0, and that indeed would make this whole thing 0, because then it would be 0 times this would be 0. So that's sort of a separate equation right here that you could solve, and this is indeed true, and then you could find out what x is. Over here, they were kind enough once again to factor, so this is also true because if this whole thing was a 0, then it would be 0 times whatever that is, and then the whole thing would be 0, which is what we're looking for, right? Solving this one, you'd have to add 1 to both sides, and then you would have that. Solving this one, you could add 1 to both sides, divide by 2, and then you have this. It is the case that this one here, you could say the sine of what angle is equal to 1. That is pi over 2, which is 90 degrees. And then we could ask ourselves here, the sine of what angle is equal to 1/2? Or the cosine of what angle is equal to 1/2? That's pi over 3, but also 5 pi over 3. So that might be a calculator problem too, where it's possible the teacher wants you to literally just plug this in and use the solve feature. Plug this one in and use the solve feature. Another way you could go about it is you could say y equals sine x and y equals 1, and then find out where those graphs intersect over here. You could say y equals cosine x in your calculator and y equals 1/2, and you could find out where those graphs intersect. So that is another approach there. I hesitate to say more about this. I could go down a rabbit hole that has to do with the unit circle and kind of understanding how you can quickly see what sine, um, the sine of which angle would give you 1, the sine of which angle, the cosine of which angle would give you 1/2. My student watching might be noting, oh, there's two answers here. That's weird. I hesitate to go down that rabbit hole because I want to keep this very close to the way the teacher is teaching it. And I will have to ask my student next time about that. Uh, Nonetheless, worse comes to worse. Understand that this could be set equal to 0. This could be set equal to 0. Then you could use your calculator to solve this equation. Okay, worse comes to worse. Same with this one. The calculator might give you a crazy decimal for these, but I'm not so sure that's bad necessarily, because the teacher did say in the beginning of this test that you can round decimals to 3 decimal places. So to me, that might be the teacher's way of sanctioning rounding answers just generally. So Anyway, let's see. Number six, the graph below consists of two lines and a parabola. Find the equation of the piecewise function. Yeah. Okay, so for this, clearly there's three parts, right? There's sort of the blue box part, there's the red box part, and then there's the yellow box part. And we'll color code this. This has to do with the blue, this has to do with the red, and this has to do with the yellow. Now, with regards to the blue box part, it's clearly happening between -2 and -1. So it's going to be -2, -1. Okay. With regards to the red part, it's clearly happening between -1 and 1. And when it comes to the yellow part, it's clearly happening between 1 and 2. Now here it's underline underneath, right? Because we have closed circle, closed circle. Here it's straight up greater than symbol or whatever the heck that is. And then over here, we have the underlines. Now, for my student watching, what's the moral of the story here? Well, the moral of the story is get clear on how many rows you're going to have, and then focus on this part first and piece that together first. Now, the question is what is the equation of this one? Well, the equation of that is going to be linear, certainly, right? And it is the case that linear equations take this form, where the m is the slope and the b is the y-intercept. Okay. Now we don't easily see what the y-intercept is. I mean, it kind of looks like it might be 3, but I'm not exactly sure. Okay. But what we do see is the following. We see that this goes through -2 comma 0, that's a point, and it goes through -1 comma 2. So we do have 2 points to work with. And as my student may recall, uh, M stands for slope. There is something called the slope formula, which is y2 minus y1 all over x2 minus x1. And you could use that, right? Or you could just count. You could say it's clearly going um, up to over to the right one. So that's probably easier, right? So that's going to be up to the right one. Okay, but then we do not know what our y-intercept is, but we know that, this is the equation of the line so far. So how could we find the y-intercept? Well, it's actually pretty easy. You just pick one of the points, for example, -2 comma 0, and you plug 0 in for y and -2 in for x. And then you could solve for b, and that would be -4 plus b. B obviously is 4. And then do not forget, you must update the equation to reflect what you just found. So that is the equation of the line of the blue line, 2x plus 4. So that goes here. Okay. Now, to recap, finding the slope was easy. We were able to get away with going up 2 over 1. That is a slope of 2. Finding the y-intercept a bit trickier. We remembered that the slope-intercept form of a line looks like this. The b stands for the y-intercept. Notice how I picked the easier point to work with. That's -2 comma 0. Any point that has a 0 in it is going to be a lot easier to work with. The y became 0, the x became -2, and the rest was history. Okay. Let's focus on the yellow one because that's easy. That is a horizontal line. Horizontal lines always take the form of y equals whatever number, whatever y value it's kind of, going through, and that's -2. So y equals -2. That means there is a literal -2 right there. And that's all there is to it. Okay, so now we're looking at this one right here. Now that's, I would say, the trickiest one for sure. It definitely looks like an upside down, like parabola, so I'm going to assume it is. And a couple things about parabolas in general. So number one, the parent function for a quadratic equation, aka a parabola, is that. And they tend to look like this, where they kind of go through the origin right here, this special point here. Now, if we were to analyze 3 points, then certainly the middle one could be the vertex, which is 0, 0. That's right here. We could also investigate this point and this point. The point on the left corresponds with -1, the x value of -1. The point on the right corresponds with the x value of 1. So we could say 1 and -1 here. And upon investigation, you would see that the y coordinates would be 1 and 1. Now, in case that's not clear, that would just be a matter of plugging in -1 into this, and you would see -1 squared is just 1, and that's why it's a 1 there. Same goes for this. So I think it's kind of helpful to understand that in a normal parent function for a quadratic function, there are sort of these three special points. And the middle one is, of course, the vertex, and then you have the flanking point over here and the flanking point there. Now, the thing you might notice here is that from the vertex, it goes up 1 over 1 to get to that point. And you could say it goes up 1 over 1 to get to that point. Now, let's focus on the right-hand point. It goes up 1 over 1. And I want you to just understand that that's sort of because there's this coefficient of 1 that's in front. Okay. Now, another way of saying that is you have up 1 over 1 happening out front. And that's sort of a trick where if you're ever graphing a parabola, if you have the um, vertex, in order to get this next point here, you could almost think of this coefficient almost like it's the slope, where this is a rise of 1 and a run of 1. So it goes up 1 over 1, and that brings you to this one. And then you could just use symmetry to find the other one on the other side. Okay. So these are just some mental notes to make. Now, I think another conclusion that we can draw is anytime you see a structure like this, where it goes from the vertex up 1 over 1, like that, in order to get to the point on the right like that, well, that means that the leading coefficient in front of the x squared is 1. So that's almost like the backwards reasoning. If you see a graph that looks like this, we know the leading coefficient in front of the x squared happens to be 1. Okay. So that's something to take into account. Now, another thing to take into account is just the various ways that functions can be transformed. For example, if you started with an x squared, but then all of a sudden you uh did a transformation on it where maybe you threw a negative out front. Well, that would take what used to be this nice upright U shape, and it would flip it upside down so that it looks like this now. Okay. So that is what the presence of this negative in front of the x squared would do to what used to be this upright U shape. It flips it upside down. So that's something to take into account. Now, another thing to take into account is, let's say you started, with one of these, but then you did something else. You um, tacked on the end a -4. Well, what that does is it takes this and it shifts it down 4. So now it's down here, okay? And it's positioned at the y value of -4 right there, okay? And the same could be said for tacking on at the end maybe a +10. Well, what that means is you used to have just a regular old x squared, but the +10 brings it up 10. So that would be up like that. And this, of course, would be at the y value of 10. Now, they might get really annoying and give you something where maybe it's a combination of things, where, for example, maybe they ask you to do a negative x squared and then minus 5. Well, this negative that's in front represents multiplication, where it's really an x squared times -1. So that's a multiplication scenario. And then over here, it's minus 5, right? Which is a subtraction scenario. So hopefully you remember PEMDAS, which is the order of operations, which insists that the order by which you do things matters, and multiplication happens before subtraction. So it, the point is with that is that you want to perform this transformation first, where it flips upside down, and you kind of do that first. So you started with this, and then it flipped upside down. There's arrows here too, by the way. Flips upside down, and that's us taking this transformation into account. Then you worry about subtracting 5. So it goes down 5 after that. So we had flipped it first, and then it went down 5 after that. And then you can kind of get rid of this thing because that's old news. And this ends up being your final thing. Okay, so this is a reflection across the x-axis, or you could say it's a reflection over the x-axis first, and then a vertical shift downward 5 units. So that's one way of handling this sort of, uh, you know, conglomeration of transformations. Okay, when there's a group of transformations, you could just remember multiplication/division occur before addition or subtraction. All right, so bringing us back to this situation, I think we can see that this right here is certainly a parabola that, maybe would have continued like that, but it certainly got flipped upside down, which would have made it so that it used to be like that, and now it's like this. But then after having flipped upside down, it went up 1 unit, didn't it? And then it ends up here, right, at the blue part. And then it looks like that. So it is a parabola that had been flipped upside down, which means there's a negative in front of the x squared. Then it went up by 1. So I'm going to say that this is the equation of this thing. All right, let me just erase these now because we don't really need them. And I feel conviction that there is a sort of 1/1 here. There's a 1/1 there. And I feel conviction about that because we have the three special points where you started at, 0, 1 right there, and then you went down 1/1 to get that, down 1/1 to get that. So that sort of implies a negative slope of down 1 to the right 1. So it goes down 1 to the right 1. So I feel confident that this slope, the so-called slope, is a -1, okay? As opposed to a -3x squared plus 1, you know what I mean? So we can feel confident that the coefficient here is not a -3/1, but a -1/1 for all the previously mentioned reasons. So that was very lengthy. It's possible the teacher provides some tricky, shortcutty way of knowing what's going on here. But for my student watching, I just want my student to know, the true reasoning process behind how we knew what this was. It was that. All right. So x squared plus 1. Should be that one. Okay. So that is the answer to this one. The graph below consists of two lines and a parabola. Find the equation of the piecewise function drawn below. Yeah, we got the blue part up here. We have the yellow one down here, and I'll even make this in yellow also. We have the yellow one here, and we have the red one now right there. Okay, so hopefully that makes sense. Hopefully this was helpful. And I will talk to you later. Bye.